Okay, so we want to first of all think about a function that has derivative 3x squared. Well, if I think about my power rule, I know that the function f of x equals x cubed has derivative 3x squared. But also, we might think, well, so does the function f of x equals x cubed plus 1, for example. So that function also has derivative 3x squared. And in fact, it doesn't matter what number we add on here, as long as it's a constant. The derivative of that constant will be 0. So one way we can write this is we can write this as f of x equals x cubed plus c, and then that will account for any constant that I add. So in fact, we find that it's not just one specific function that has derivative 3x squared, but it's a whole family of functions. Anything that looks like the form x cubed plus any number will have derivative 3x squared. So we get kind of a family of functions actually there for our derivative. So here it says the indefinite integral. So what we want to say here is the notation, the integral of f of x dx is equal to capital F of x plus c for some capital F of x such that capital F of x prime is equal to little f of x. So in other words, i.e. capital F of x is an antiderivative of f of x. Okay, and so what we have here is the idea that this notation with this integral symbol is standing for this idea of an antiderivative, or a function that has derivative little f. So that may seem a little bit surprising, because before we had introduced the idea of this integral symbol talking about maybe a rate of change, the sum of a rate of change, or an area. And so it may not be clear why that is linked to the idea of an antiderivative. And so that's why in the next section we'll talk about the fundamental theorem of calculus, which gives us that relationship between integration, this idea of area, and derivatives, which is the idea of rates of change, and how those two things are kind of opposites of one another. So we'll be talking more about that, but it should be a little bit surprising right now that there's this connection. Okay, so let's keep going. So here, to be able to evaluate this indefinite integral, I need to find a function that has derivative equal to 15x to the fourth minus 3x squared plus 17x minus 1. Okay, so to start, I know that if I had the function 3x to the fifth, that when I took the derivative of it, I'd get 15x to the fourth minus, and this one is going to end up being x cubed. And so you may have to spend a little bit of time thinking about why this is the case. So if I want 17x to be my derivative, I know the power's got to go up. It's going to be an x squared, but when I bring that 2 down, I need to get 17. So what I really need is 17 over 2. So that when that 2 comes down, I just get a plain old 17 minus, and then something that has derivative 1. Well, I know that x has derivative 1. Derivative of x is 1. And then I also know that any constant could be added there, and then that when I take the derivative, that constant will go to 0, so I could have this plus c at the end. Okay, so then I want the power rule for integrals. So we were just kind of talking about that. I know that the power of x is going to go up by 1, because when I take the derivative, the power goes down 1. And then I need to, the coefficient is going to be 1 over n plus 1, because when I bring that n plus 1 power down, I need it to have something to cancel with, so that I end up getting just a plain x to the n in front. And then I'll need a plus c on there, because that could be, any constant could be added there, and that wouldn't impact the derivative. There's one other little thing we need to consider here, and that is that if n is equal to -1, I'd get a 0 in the denominator there. So this is true for n not equal to -1. And on the next page, we'll deal with what happens when n equals -1. Okay, this idea of linearity is like the idea of breaking up into pieces. So if I have two functions added there inside of my integral symbol, I could do them individually. And we were just using this in the previous one because I was doing it piece by piece, right? I was looking at an antiderivative for each piece. So I was utilizing this linearity rules that I could break it up into pieces. And then here I've got the c times f of x. I can pull that c outside. Okay. And an antiderivative of 1 over x. So again here I want to be thinking about, well, we kind of have an idea that it might be natural log of x. So the integral of 1 over x dx equals natural log of x, but we have to do a little bit of an adjustment here because natural log of x is only defined for positive values of x, and so 1 over x is actually defined everywhere except x equals 0. So what I need to do is I need to do the natural log of the absolute value of x so that I can plug in like negative values of x and still get something. And so that function looks like this. So that absolute value is going to allow us to plug in values into natural log that we couldn't plug in before because we can't plug in negative values. So you just might think about that absolute value is kind of to adjust for this idea that natural log is only defined for positive values. So you can also write this as integral of x to the -1 dx is equal to natural log of absolute value of x plus c. Oh, I do want to go back and make a note that for the power rule, remember we had said that this power rule only worked when if n is not equal to -1. Well, if n equals -1, then we have this case, right? So we get that it's the integral of x to the -1 is natural log of x plus c. So so this power rule is going to hold everywhere except n equals -1, but when n equals -1, then I get this natural log thing going on. Okay, so for our basic trig integrals, we can kind of, if you look back at like a derivative table, you can kind of just do it all backwards, and you can see that the integral of cosine x dx is equal to sine x plus c, and the integral of sine x dx is going to be negative cosine x plus c, and then the integral of secant squared x dx is going to be tangent x plus c. And then for the integral of tangent x dx, well, you're going to deal with this in Calc 2. So I'm just going to leave it at that for now. You don't need to know that one for this class, but you'll talk about that some in your Calculus 2 class. And we can probably do it once we get u substitution, but we'll kind of, so let's just say later for now. We'll do that. But for now, we're just kind of looking at our derivative table and kind of doing the opposite. So the integral of cosecant x cotangent x dx should be equal to negative cosecant x plus c. The integral of secant x tangent x dx will be equal to secant x plus c. And the integral of cosecant squared x dx is equal to negative cotangent x plus c. And again, for what I'm doing here is just kind of using my derivative table, but thinking about it backwards like an antiderivative. Okay, what about integrals involving e to the x? So the integral of e to the x dx, an antiderivative of that is just e to the x plus c. And an antiderivative of e to the kx is going to be 1 over k e to the k x, and then plus c. And again, remember, when we take the derivative of that, that k is going to come down as a coefficient, so we need the 1 over k there to cancel that out. Okay, so let's do some examples. So here I have 5t to the minus 1 minus 3t to the minus 2. So again, I'll have 5. That's by the linearity rules. That 5 can just stay put. An antiderivative of t to the minus 1 is going to be natural log of absolute value of x. And then minus, the 3 can stay put. And an antiderivative of t to the minus 2 is going to be t to the negative 2 plus 1. So it's going to be t to the minus 1. And then I'm going to divide by minus 1. And then plus c. So this is going to simplify to 5 natural log x, natural log of absolute value of x, plus 3t to the minus 1 plus c. Okay, and the next one, we have an antiderivative of y to the 6 over 11. And so that's going to be y to the 6 over 11 plus 1, and then divided by that new power. Well, let's think about what that is. So 1 would be 11 elevenths. So that'll be y to the 6 plus 11. So what's that, 17 elevenths? And then if I do 1 over 17 elevenths, that's 11 seventeenths. And then plus c. This one, you might think, oh, it looks like a product inside there. Maybe we need something like product rule. And we actually will have something like product rule for integrals. It's going to be called integration by parts, and that's something you'll do right at the beginning of Calculus 2. So we aren't going to have anything like product rule yet, but what I can do is just multiply that x in and then use my linearity rules. So without doing anything yet, I'm just multiplying in. I'll get x cubed minus 4x dx. And now I can integrate that just using my linearity rules. So I'll have 1/4 x to the 4th minus 4 over 2 x squared plus c. So that would be an antiderivative. Okay, for this one, again, it looks like you might think, oh, I need something like quotient rule, but we're not going to have anything like that for integrals, but what I can do is just divide each thing by x squared. And so that will give me the integral of x plus 3x over x squared will just be 3x to the minus 1. And then minus 4 divided by x squared is going to be minus 4x to the minus 2. And then all of that is multiplied by dx. And then I'll get that equals. So an antiderivative of x will be x squared, 1/2 x squared, plus 3. An antiderivative of x to the minus 1 is natural log, absolute value of x. And then minus 4 over, so when I do x to the minus 2 and I add 1 to the power, I'll get x to the minus 1 and then divide by minus 1 and then plus c. And you can simplify those coefficients if you want. Similar thing here, I have this 12 minus z over square root of z. So what we're going to do is we're going to start by just simplifying everything. So I'll get 12 over square root of z minus z over square root of z dz. And then if I simplify that, I'll get integral of 12z to the minus 1/2, because remember, a square root is the same as a 1/2 power. And since it's on the bottom, I can write that as a negative exponent. And here I'll have minus z to the, well, it's z to the first 1 minus 1/2, so that'll just be z to the 1/2 dz. And then I can use my power rule for antiderivatives, and I can get 12z to the 1/2, and then I'm going to divide by 1/2, which is the same thing as multiplying by 2, minus, and then I'll have z to the 3/2, and then I'm going to divide by 3/2, which will be 2/3, plus c. So then I'll have 24z to the 1/2 minus 2/3 z to the 3/2 plus c. And if you're ever wondering, like, did I do this correctly? What you can do is just take the derivative and see if you end up back where you started. So that's a good way to check yourself, since you're used to taking derivatives a lot more than antiderivatives. Okay, for this one, again, if I took the derivative, the 5 would come down, so I need to account for that by doing 3/5 e to the 5x plus c. So if I took the derivative, the 5 would come down, cancel with that 3/5, and then I would just have 3 e to the 5x. So that's an antiderivative. This one says tangent theta times cotangent theta. Tangent theta times cosine theta. So what I'm going to do is I'm going to start by just simplifying what's going on the inside. So tangent I can write as sine theta over cosine theta, and then I'm multiplying that by cosine theta d theta. So this cosine over cosine, I can cancel that because cosine over cosine is equal to 1, and that's just the integral of sine theta d theta. Well, and I know that I want to find an antiderivative, so I know that the derivative of cosine is negative sine, so an antiderivative of sine would be negative cosine theta plus c. Okay, and here I have x squared plus secant squared x. So if I want an antiderivative of that, I'll have 1/3 x cubed plus, what has derivative secant squared? Well, I know that the derivative of tangent is secant squared plus c. The next one says verify this statement by using integration. Okay, so what I want to do, or using differentiation. So what I want to do is I want to show that the derivative with respect to x of negative 1/4 x plus 13 to the minus 4th plus c. Well, what is that derivative? I want to show that that derivative is equal to this thing that's inside there. So let's try to show it, but we're going to use differentiation. So let's try it. So if I take the derivative using the chain rule, I'll have negative 1/4 times negative 4 x plus 13 raised to the power, I have to subtract 1, so negative 4 minus 1 will be negative 5, and then times the derivative of the inside part. The derivative of x plus 13 is just 1, and then the derivative of c is 0. And so this becomes the minus 1/4 times 4, and then two negative signs are going to make it positive, so I'm just going to be left with x plus 13 to the negative 5. And that is, in fact, what was inside this integral to begin with. So that is, so that means that this statement is true. Okay, let's try it again with this one. And so I have, so what I want to do is take the derivative with respect to x of 1/12 times 4x plus 13 cubed. And so if I take the derivative of that using the chain rule, I'll have 1/12 times 3 times 4x plus 13 to the second power. And then times the derivative of the inside is just 4. Oh, sorry, that should be 1/12. Okay. And so then plus the derivative of c, plus c, the derivative of c is 0. And so what do I get? Well, I have a 1/12 times 3 times 4, so that ends up making a 1. So I'll just have to be left with 4x plus 13 squared. And that actually checks out that this is equal to what I started with. So that makes that true. Okay, now I'm told that a car traveling with velocity 24 meters per second begins to slow down at time t equals 0 with a constant deceleration of -6 meters per second squared. So it asks me to find a velocity function at time t. So what I know is that my acceleration, so I know that the derivative of velocity is equal to the acceleration, right? In other words, velocity is an antiderivative of acceleration. So if I know that my acceleration is equal to -6, then my velocity function should be an antiderivative of acceleration. So if I find an antiderivative of that, that would be -6t plus c would be my velocity function. But I also know that at time t equals 0, I know my velocity at 0 is equal to 24. So I can actually, in this case, figure out what that c needs to be by plugging in 0. So if I know that my velocity function is v of t equals -6t plus c, and I know that if I plug in 0 for t, I should get 24, I can plug in the value I know. That tells me that c equals 24. So in fact, I have a precise value for that constant in this case because I knew that my initial velocity was 24. So my velocity function is going to be v of t equals -6t plus 24. Then it says, find the distance traveled until the car comes to a halt. So I know that my position function, so when does the car come to a halt? So when is v of t equal to 0? So I can set v of t equal to 0, -6t plus 24 equals 0. So I can subtract that over, and I get that t equals 4. So I know the car stops at t equals 4 seconds. But it's asking for the distance traveled. Well, how is distance traveled related to the idea of velocity? So I know that that the distance traveled is an antiderivative of velocity, because when I take the derivative of position, I get velocity. So that means that position is an antiderivative of velocity. So my s of t should be equal to an antiderivative of v of t dt. Well, I have a function for v of t now. So that's going to be an antiderivative of -6t plus 24 dt. And so what is that? Well, that's going to be -3t squared plus 24t. And then I could have some plus c, but I'm just going to let my initial position be 0. And I want to evaluate s of 4 seconds and see how far it's traveled from the initial spot of 0. So -3 times 4 squared plus 24 times 4. And I can plug that into my calculator. Let's see what we get. That gives us 48. And if you look at the units of acceleration, it's meters per second squared, which means that the units of position are going to be in meters. So the position at time 4 seconds is 48 meters from the starting position of 0. So I know that it's traveled for 48 meters. This semester, which is the spring 2025 semester, we're going to not do these initial value problems with differential equations, and that's just because we had those snow days, and so we're just going to go ahead and skip those problems for now, but that's the end of that section on antiderivatives.